So now we can go to postulate 2, which says that, and postulate 3, for every property of a system, there corresponds an operator which must be Hermitian. Okay? So there's an operator. If there's a property of a system, there's an operator corresponding to it which must be Hermitian. If the property is measured, okay, we're going to postulate that the only possible outcomes are the eigenvalues of the operator. Okay? And like I said, we want Hermitian. So here it is, the reason now why we want it to be Hermitian. The reason the operator must be Hermitian is we've already proven that Hermitian operators have real eigenvalues. And we are going to postulate that, so when we postulate, that means we're going to assume, okay, that the only outcomes of any measurement will be eigenvalues of that operator. So, what are these operators? Quantum mechanical operators corresponding to position are just multiplicative operators, which multiplied by the function by the coordinate. So let's say if you're going to define x1, y1, and z1 as the coordinates of particle 1, then, okay, the operator x1 hat simply multiplies whatever function it operates on by x1. It's a multiplicative operator. Okay? So what would be the expression for the operator that corresponds to the y-coordinate of, let's say, particle number 3? Y-coordinate of particle number 3 is y3, right? Y sub 3. So to define the operator, when you say then y3 hat, if it were to operate on a function, it will just give me back y3 times the function. Okay, so you say y3 hat is a multiplicative operator. Now let's look at linear momentum operators. Okay, the quantum mechanical operator that corresponds to the x-axis component of the momentum, that is p sub x, okay, of particle 1, transforms any arbitrary function as follows. So this is the operator for the x component of the momentum of particle 1. What is momentum? Mass times velocity, right? So the momentum p sub x is mass times velocity along the x-axis. Okay? So if you're dealing with multiple particles, then you have to specify which particle you're dealing with. So let's just put a 1 there. I mean, to emphasize with one particle 1, there might be other particles in our system. Okay? So px1 hat operating on the function, this is what it does to the function. It takes the derivative of the function with respect to x1 and then multiplies it by h bar over I. Okay? H bar is just Planck's constant divided by 2 pi. Okay? And I, of course, is just square root of -1. Note that this is a Hermitian operator. Remember we said the derivative operator is not Hermitian? But if you multiply it by I, it becomes Hermitian. That's why you have that I there. Okay? So that this I in this expression makes this overall operator a Hermitian operator. So that is the operator for momentum. That is, you need something, that's something you have to memorize. Okay? H bar over I derivative with respect to the coordinate. So H bar over I times the derivative with respect to whatever component, x, y, z, or whatever. Okay. One memory aid I use to remember that is hider. Okay. Hider, derivative. Okay. So, what would be the expression that defines the operator corresponding to the z-axis component? Okay. So, z-axis component of the momentum. So, p sub z of particle number 2, so z2. Okay, so what's that operator going to be equal to? If I operate that on a function, what do I get? I take the derivative of the function with respect to z2, okay? And notice it's a partial derivative because your function may be a function of more than one variable with respect to z2 times, after you get the partial derivative, you multiply by h bar and you divide by I. Okay, so that is the momentum operator along the z-axis for particle number 2. Okay, kinetic energy operator. Kinetic quantum mechanical operator corresponding to kinetic energy is given by this expression right here. Kinetic energy, or you can say K, if you want. I think your book uses K. What's K? 1/2 mv squared, right? And if I multiply that by by m over m, still the same, right? And so that's 1/2 m squared v squared over m, right? And you can see, so that's in classical mechanics. And that's just going to be, what's mv squared? That's just p squared. So this is going to be p squared over 2m. In other words, what we're really saying is, okay, we know what p is, right? So let's just say our particle just moves along one dimension. So you can just say then that t hat is just p hat, that's p squared divided by 2m. Okay, so this is a kinetic energy operator. So what would this be? If we were to apply t hat on a function, what would we do? P hat over 2m applied on a function. P hat, that's p squared, right? Applied on a function. Okay. So what is p hat applied on a function? H bar over I, derivative of the function with respect to, let's just use the full derivative. Let's just assume we have one dimension, one variable. So derivative of f with respect to x, right? And we're still going to apply p hat on that one and divide it by 2m, right? So what do we get now? I can pull this out of my integral, right? Out of my derivative. That's a constant. P hat is a linear operator. I can pull that out of a linear operator. So that's going to be h bar over I. And p hat is what? P hat is h bar over I derivative with respect to x of this one right here, df dx, right? That goes in there. And the whole thing is divided by 2m, right? Still have that 2m right there. So what do I get? H bar squared over I squared, right? Times 2m. I'll factor out all the constants. Okay. And what do I have here? That's just the second derivative with respect to x of m. Okay, so that's, what's I squared? -1. So that's negative h bar squared over 2m, second derivative with respect to x of whatever function you're operating on. So this is your t hat operator. This is for due to motion along the x-axis. Okay, one-dimensional problem. And if you have multi-particles, then you may have to specify which particle, 1, 2, or 3. Due to motion of particle 1, then you'd have to say, okay, then if you have, okay, due to motion of particle 1, and you use partial derivatives if your particle can move along the x, y, and z axis. So this is just the part of the kinetic energy operator that deals with motion along the x-axis for particle 1. Okay? So notice this is negative h bar squared over 2m1. That's mass of particle 1. Okay? If you have another particle, then you have to use the mass of the other particle for that operator for that particle with respect. And you have the second derivative with respect to x1. So that's a kinetic energy operator. So what would be the operator that corresponds to the total kinetic energy of particle number 2? Well, total kinetic energy would be what? Total kinetic energy would be p squared over 2m, right? But we're dealing 3 dimensions here. We're dealing with 3 dimensions. So what's the square of a momentum vector? P sub x squared plus p sub y squared plus p sub z squared, right? Divided by 2m. So that's the classical expression. So in quantum mechanics, what do we say? The kinetic energy operator is equal to px squared over 2m is what? Negative h bar squared over 2m. And this is particle number 2, so I'm going to call that m2. Okay. Second derivative with respect to x2. Okay. That's px squared over, so this is your t sub x. 2. Plus negative h bar squared over 2 times mass of particle number 2 times second derivative with respect to y2. So this is ty for particle 2 plus negative h bar squared over 2 times mass of particle 2, second derivative with respect to z2. Okay? So that's your kinetic energy operator, just for particle number 2. So this is T sub z for particle number 2. Okay? We can simplify this. We can factor out negative h bar squared over 2 times mass of 2. What do I have inside? Second derivative with respect to x2 plus second derivative with respect to y2, sorry, plus second derivative with respect to z2. Okay? This expression right here is called, you can abbreviate that by an inverted triangle. This is called the del squared operator. Del squared. Okay? So whenever you write del squared, and this is del squared for particle number 2. So I'm going to put a label there that says 2. Okay? So a sum of second derivatives along the x, y, and z axis is called the del squared operator. You got it? There. I have it right here. Del squared or Laplacian. Okay, so del squared for particle I is just the derivative with respect to x sub I, second derivative, plus the second derivative with respect to y sub I, plus the second derivative with respect to z sub I. Note that each of these can be thought of as an operator. So you say it's like operator A plus operator B plus operator C, right? So you can just distribute that. So that applies to that function, that applies to that function, that applies to that function. So, okay? So this is going to be AF plus BF plus CF. Okay, so what's the expression that defines the operator corresponding to the total kinetic energy of the nucleus and 3 electrons of a lithium atom? So you have a nucleus, let's call that N, and electron 1. So, and you got electron 2, and you got another electron, electron 3. Lithium atom has 3 electrons, right? And a nucleus. So what's the total kinetic energy? Total kinetic energy is just equal to kinetic energy of particle 1, which is the nucleus, kinetic energy of the nucleus, plus kinetic energy of electron 1, plus kinetic energy of electron 2, plus kinetic energy of electron 3. Okay? If I were to expand this, What's kinetic energy of the nucleus? Negative h bar squared over 2 times the mass of the nucleus, del squared for the nucleus. Right? What is kinetic energy for particle 1? Negative h bar squared over 2 times the mass of an electron. Okay, you have the 3 electrons, so no, this is mass of the nucleus, this is mass of the electron, okay, times del squared for electron 1, right? And then you do the same thing for electron 2 and electron 3. You can just factor it out, plus del squared for electron 2, plus del squared for electron 3. So you can see this expression can get really hairy. It can get really wrong. No, because those are separate, different things. This is with respect to the coordinates of x1. This one is with respect to coordinates of x2, and that's coordinates of x3. Okay? So that is the total kinetic energy of a lithium atom.